Hi, this is Paul Bamberg. I learned how to use R in conjunction with putting together and teaching Mathematics E156 for the Extension School. This video is to show you how, even if you've never used R in your life before, you can use it to work with the normal distribution in Mathematics E3. Here is an R script that I've written that you can get off the website. And to run a line of the R script, all I do on my Windows computer is hit Control R. You can see the cursor moving down the screen. Any line that begins with a number sign is just a comment and doesn't do anything. Here's a line that doesn't begin with the number sign. It says rnorm1, and rnorm is an abbreviation with R for random and norm for normal, and it's asking me to generate one sample from a standard normal distribution. If you look down at the bottom of the left-hand side of the screen, you'll see that it generated the number minus 0.86 and change. Now I can do the same thing again. I will store the number that I generate in a variable named x, and then after the semicolon, x will just print that out. So I got a different result. And that's the main point of the rnorm function. Every time you call it, you get a different randomly generated number, but these numbers are generated in accordance with the standard normal distribution. If I want more than one number, I just call rnorm on 10, and now I get 10 numbers, some of them positive, some of them negative. If I want 10,000 numbers, I don't want to display them all, but R will generate them in a flash. Head of x prints the first 6, so I can see that I'm getting some numbers, some of them positive, some of them negative, most of them smaller than 1. If I want the average of those 10,000 numbers, which are now stored in x, I call the function mean, and I get a number that's 0.01, pretty close to 0. If I ask for the variance of those numbers, it will do a computation that you probably know how to do with the 10,000 numbers. Give me 0.98, which is pretty close to 1. If I want to look at all the numbers, the obvious thing to do is to plot a histogram, and the R function hist will do that. That shows, for example, that near 0 we've got a couple of bins that had numbers in them close to 2,000 times. If I want smaller bins, I discovered experimentally that breaks equals quote FD does the job. So there's a more detailed histogram. And if I want to show something that I can compare with the bell curve for the normal distribution, I just say prob equals 2. Now you see the vertical axis is labeled with something called density, and this has the property that the combined area of all the bars in the histogram is equal to 1. So that was rnorm. There's always a family of 4 functions for any type of distribution, and here's the one that begins with a D. It's dnorm, D for density, as in probability density. And I can ask, what is dnorm of 1.05? It's 0.229. The best way I can think of to interpret that is it's the expected height of a bar on the histogram that you're looking at, and I can check that by using the R function abline. Now abline is designed for plotting numbers in slope-intercept representation, with A representing the intercept and B representing the slope. A special case is a vertical line, and I get that special case by saying V equals 1.05. I want to plot this in red, and you see it there on the histogram, a vertical line at 1.05 on the histogram. Now I'm going to plot a horizontal line with H equal dnorm of 1.05. And you can see that where the red and blue lines cross is pretty close to the top of that bar in the histogram. I can do this for all values on the x-axis by using the curve function. So curve will plot a graph of dnorm of x. Add equals true means it gets overlaid on my histogram. Col equals red has it plotted in red. And isn't that beautiful? There is the distribution of x plotted as a density function, with which you're probably already familiar, and you can see that it agrees very nicely, though not perfectly, with the histogram. So you can think of the dnorm function as specifying what a histogram will look like, and you'll get better and better agreement if you have a large number of samples. Let's try that. Let's generate 100,000 samples. Takes almost no time. Plot the histogram, plot the curve, and we have an almost perfect matchup. Third function in the family is pnorm. P is for probability, and this function specifies the probability that a random variable x generated from the standard normal distribution has a value that is less than or equal to a. So pnorm of 1.05 specifies the probability that x is less than or equal to 1.05. That came out to about 0.85. And a nice way of visualizing that is to plot a vertical line at 1.05. You could notice that about 85% of the area under the graph is to the left of that line. But there's another way of doing it with our samples. Now this is a bit tricky. X less than or equal to 1.05, according to R, has the value 1 if it's true, has the value 0 if it's false. So if I ask for the mean of the quantity x equals less than or equal to 1.05, I will get the mean value of a function that's 1 only if x is less than or equal to 1.05. That is, I'll get the probability that x is less than or equal to 1.05. And that came out to 0.85096. Not exactly the same, because this is based on the actual data, not on the probability distribution. This is the fraction of the time in our 100,000 samples that x turned out to be no greater than 1.05. If I want to find the probability for x to be in some interval, I just have to use this pnorm function twice. First, I find that it's got a probability of 0.158 of being less than minus 1. It has a probability of 0.841 of being less than or equal to 1. Or if you want the probability that it's greater than 1, you just say lower dot tail equals false, and you get a probability of 0.158 of being greater than 1. If I take the difference between the probability of being less than 1 and the probability of being less than minus 1, I get the probability of being in between minus 1 and 1, which, as you very likely already know, is 0.68. I can illustrate that graphically in two different ways. First, I could do a plot of pnorm as a function of x, showing that the probability of being less than minus 3 is pretty close to 0, while the probability of being less than 3 is pretty close to 1. And by drawing horizontal lines at minus 1 and plus 1, I can show the probability of being less than or equal to those values and indicate that that probability is 68.3%. Here's a more conventional way of doing it using dnorm. I plot a curve showing the normal density. I plot vertical lines at minus 1 and plus 1. Since we know that the probability of being in between minus 1 and plus 1 is 68.3%, I can use that text to label that region, and I can also label the regions less than -1 and greater than +1 with 15.9%. You might find it useful to make such plots in conjunction with doing your homework, and the export item at the top will allow you to take a graph like this and export it as a JPEG or PNG file that you could include, say, in a homework assignment. Now let's check this idea using 100,000 samples. Generated 100,000 samples. This calculates what fraction of those samples are less than or equal to -1. Sure enough, it's about, though not exactly, 16%. In between -1 and 1, about 68%. Greater than 1, about 16%. However, I want to warn you, you need a lot of samples to get good agreement between the actual selection of samples and what's predicted by the probability distribution. If I do the same thing with just 100 samples, I get something that's not too far from 16%, but actually 19 of the 100 samples turned out to be less than -1. Only 63% of them turned out to be in between -1 and +1. And 18% of them turned out to be greater than 1. It's worth playing with R on your own to get an idea of how many samples you have to take before the probability distribution accurately predicts what's going to occur when you take a large number of samples. It takes more samples than you might ever have guessed. Finally, there's a fourth member of the norm family, Q-norm. Q is the first letter in quantile, and what this specifies is what value of x you need in order to get a given probability that the number you generate will be less than or equal to x. So Q-norm of 0.7 answers the question, how large do we have to make x in order to get a 70% probability that our random number will be less than that? The answer turned out to be 0.5244. And if I ask what's the probability that a random, normally distributed random variable will be less than 0.52, the answer is very nearly 70%. I think the best known example of this is what value will cause x to be greater than that only 2.5% of the time. In other words, what is Q-norm of 97.5%? The answer is 1.959, very close to 2. And I can illustrate that conclusion again using the dnorm function. I plot it. I draw a vertical line at -1.95, another one at 1.95, and now I can say that 95% of the time my normally distributed random variable will be in between the blue lines. 2.5% of the time it will be to the left of the left blue line or to the right of the right blue line. Now let's finish up by doing a slightly more general normal distribution specified by two quantities that are frequently represented by the Greek letters mu and sigma. For a standard normal distribution, mu is equal to 0 while sigma is equal to 1. But I can specify by using mean equals a value of mu that shifts the center of the distribution. So here is a plot of the normal density function with mean equal to 2. You can see it looks just like the standard normal distribution, except that it's centered around 2 rather than around 0. If I plot the standard normal distribution, remember add equals true, we'll get something to plot on top of what you already have shown as your graphic. You can see the shift of 2 units to the right. If I specify a standard deviation, like SD equals 2, again, I get something that looks like the standard normal distribution, only it's spread out along the horizontal axis by a factor of 2. If I ask for the probability of getting a value less than or equal to 3 when the standard deviation is equal to 2, I can show that on my graph. Happens 93.3% of the time. But I could have done the same thing with the standard normal distribution. I could have asked, what's the probability of getting less than or equal to 3/2? Again, it's 93.3%. And apart from the labeling of the horizontal axis, the graphic looks exactly the same. That's why someone armed with a table of the standard normal distribution can basically figure out things about arbitrary normal distributions with whatever mean, whatever standard deviation they want. Now, if we draw a large number of samples from any normal distribution, we can predict what the mean and standard deviation for that sample are going to be. If I draw 10,000 samples from a normal distribution with a mean of 3 and a standard deviation of 2, I expect that the mean of those samples is going to be close to 3. Sure enough, it turned out to be 3.01. I expect that the standard deviation will be close to 2. 1.978 is pretty close to 2. And the square of the standard deviation, the variance, should be close to 4. But notice, even though this is a large sample, 10,000 random numbers, I don't get exactly the parameters of the distribution. If I plot a histogram of those 10,000 samples, I get something that is very close to the graph of the normal density function with a mean of 3 and a standard deviation of 2, but I don't get a perfect matchup. Nonetheless, about 68% of my samples are within one standard deviation of the mean, and I can check that by drawing vertical blue lines at one standard deviation above and one standard deviation below the mean. If I then take an expression to which r attaches the value 1, if x is greater than 3 minus 2 and x is less than or equal to 3 plus 2, I get something that's close to 68%. I can do the same thing with the actual probability density function. I can ask, what is p norm of 3 plus 2 for this distribution? What is p norm of 3 minus 2? The difference of those two function values is precisely the probability of being within one standard deviation of the mean, namely about 68%. So that concludes this little introduction to how to use R to work with the normal distribution. Any graphs you want, any numbers you want to compute, R will do it for you, and it is, in my opinion, much easier than looking things up in old-fashioned tables of the standard normal distribution.